I built this 6-axis robot right here, piece by piece, on my desk. It's based on an open source design, but I re-engineered some of the parts, I found where to buy all the components, I did the assembly, wiring, and programming myself, with the goal of making a robot arm that I can actually use for a wide variety of projects. In this video, I'll go over the design, 3D printing, assembly, wiring, programming, and of course, you'll see me test it. So let's jump right in. Alright, so first let's start with the design. This robot has a joint at the base which allows you to rotate the whole base, as you can see here. Then has a shoulder. You can see it's driven by 2 stepper motors. The stepper motor rotates, which they have belts that wrap around this other part, which cause this whole joint to rotate. We then have over here the elbow, similar setup except one motor. So here's the motor. This one is a motor with a planetary gearbox that has a shaft, and then it goes through this pulley. The belts wrap around this piece, which allows this joint to move. Then we have another joint here, which basically allows this joint here to rotate like that. This whole thing can rotate about this axis, which can be super useful to reach the desired endpoints that you want to do with the end effector. Now you might ask, how's that happening? Basically, inside of this, we have a motor hidden. So this motor has a coupler that then attaches to a threaded rod. You can see it has bearing on both parts. There's a gap between the 2 3D printed parts, and then there's a nut that will secure this part, but it also have the shape to cause this other portion to rotate whenever you rotate the shaft through the motor. So that allows this whole piece to rotate. We then have another joint here with this motor here that basically causes this joint to rotate. You have the pulley, the motor, and you can rotate this any way you want. And then you may ask, what is the 6th axis? That's this over here, similar to the other one. There's a motor hidden, and as you give it power, this shaft will rotate. So those are the 6 joints. Here we have the end of arm tool. Right now I have it set up with a camera. I have a video on this, watch it if you haven't. Basically it's a Raspberry Pi HQ camera with a 16mm lens, and these are flexible gears that are on a micro stepper motor that basically allow me to change the focus and aperture on the camera. The rest of the design, right, we talked all the motors that cause each of the joints to move. This has belt tensioners. So the belts are not shown. The original design for this robot was based on basically setting this housing that hosts this motor and then pushing it all the way along the slots to the left. I'm using a wooden board, and making slots is not super easy. Plus, I much rather use a tensioner than having a clamping force be what defines my tension on my belt. So I put a belt tensioner there. We have belt tensioners here inside of these joints. And so basically you have a tensioner on anything that is belt driven, which is the base, the shoulder, the elbow, and this other joint over here. This rotation and this rotation are all direct driven attached to the shaft, so you don't need any belts or tensioners there. Over on the electrical, so if we focus first on power, we have a power supply along with a housing. Here I don't have it in the design, but we have a switch, and I take the power coming out of that, route it through a hole. And now we take it to the top of the machine. This is a cover that goes along with this fan that will cool everything inside of it. The fan will be powered by 24 volts and will flow air this way. You could also set up to pull air, but it will cool everything inside. This is a power distribution strip with fuses. It basically takes the inlet of the 24 volts coming out of the power supply. Some components are operated by 24 volts, such as these 3 main stepper motor drivers, which power the shoulder, the 2 motors in the shoulder and the elbow. And we also have 24 volts for the fan. This is a 24 volt to 12 volt converter, which will power up our ramps 1.4 board that it's a hat to the Arduino Mega, which will have inputs to connect stepper motor drivers. I'll be using some TNC 2208, and those are wired for each of these. So for the base motor, for the one that rotates around here that it's hidden, for this one over here that you saw, and for the one over here that it's hidden. So those are the 4 stepper motor drivers that will be powering those joints on the robot. So main differences versus the open source design is the fact that I used different stepper motor drivers. They had a different version of the stepper online drivers. These are a bit newer. Additionally, I showed you how the belt is normally tensioned by putting this and sliding it to the right. I just went ahead and added a tensioner, and then I added the 6 axis over here. Now that also had been done with the RBX1, which is the variant of the Movio open source design. I think they used it in NEMA 14. I put a NEMA 17 inside, mostly because I had it lying around. So I redesigned this joint specifically to host that motor. The only other difference, of course, is the fact that I used a bigger enclosure to go with this stepper drivers, and which also went with a bigger fan. And of course, that I added the ULN 2003 for the camera setup. Now this GitHub page has the official open source design from BCN 3D Movio. Movio being the 5-axis robot that is open source, that has the bill of materials, CAD files, STL files for you to print, user manual. You can see here has full description, instructions on how to assemble, etc. And it even comes with the bill of materials. Now you can see this is the one for the 5-axis robot, right? The one I did has a cutout here, and it adds the 6-axis via motor. So this open source design is based on the one that is 5-axis. Now, there's a remix of that design, which is the RBX1. Robotours used to sell a kit. Looks like it's sold out, or maybe they haven't sold it in a while, but basically they sold you most of the parts so you could just 3D print some things and then get to building. I don't think they offer that anymore, but they do have here a pretty useful set of also links and resources that are available, right? You can download the STL for their files that comes with the 6-axis, or you could just redesign your own based on the Movio files, and then assembly instructions, as well as some helpful videos. Now I also went ahead and set up some Amazon pages where you can find all the components that I used to build my version of it, right? So this is the Stepper Online driver that I used, the TMC 2208s, the specific motors, all the electrical, right? The Arduino Mega, the RAMS 1.4, that's a hat to the Mega, power supply, the switch, main cable that connects to the switch that enables you to power the power supply, etc., etc. I have all that, and I'll have links in the description to the video. So I bought most of the things from Amazon. The only exception being I bought a few bolts from Bolt Depot. Amazon, as you see here, has many kits for metric 3mm, 4mm, 5mm, but you do need an 8mm bolt and nylon nut that I didn't feel like buying a whole kit, a bit more expensive than buying individually from Amazon, so that worked great. So overall, it was good for buying just a single bolt. All the 3D printed parts were printed with my Elegoo Centauri Carbon, and it took about 100 hours of total print time, 3.5 kilograms of filament, which were mainly ABS and ASA, with a few of the low force, low heat parts printed with PLA. So we'll start the assembly at the robot's base. We then move over to the second joint, and we ensure to set up the belt tensioner for this joint, as we will also do for the rest of the joints. We'll have to set up threaded inserts to enable us to put bolts to add tension to the belt tensioners. And then we'll connect the driven portion of joint 2 to the portion that would hold the pivot point of joint 3. And we'll work our way up through the assembly. Over here in joint 3, we're going to be setting up the motors, belt tensioners, etc. to set up the full joint. And then further up the arm, we're going to be setting up the motor and coupling to enable the rotation of the 4th axis. And we'll set up the 5th link or 5th axis with that rotation of the wrist, and this part that has the internal motor then enables that 6th axis rotation. We'll need to make sure to set up the internal bearing and nut to join these two parts together. Basically, you insert it and you start to thread it and rotate. Just ensure that you do leave a little bit of a gap so that you don't have friction as the joint rotates. Close this guy. On the wooden base of the robot, we'll have to ensure to map out all the holes we're going to make, and then go ahead and start drilling and cutting out the circle so that we can then mount all the components. Once done, we can start setting up the robot on the actual wooden board. So I'll place it here. Make sure to set up the belts for every joint that is belt driven before you set up the shaft that would hold the joints together. Insert the shaft. These bolts over here, ensure that you set up base 2 and fully attach it to the rotating base of the robot. And we don't want a bunch of wires dangling around, so we're going to go ahead and bolt them up so that we can get a clean look once we're done. And then I tie the zip ties. Now I'll go ahead and cut them. And now we'll set up all the electrical, all the stepper drivers, or the Arduino, the RAMS 1.4, and the power, etc. So let's go ahead. We set up the TMC's 2208s. There it is. Got the output cable bundles coming out on the Arduino Mega. Here you have to connect power and flip on and off. Now let's go ahead and set up our gripper. You don't have to print in different colors, but I did to get a better look. We start by setting up the servo to the bottom of the base and the main linkage that will drive the gripper to open and close. And when attaching the final link, make sure you set that gear to make contact at a spot that will enable all the links to open and close in a parallel manner so that it doesn't look crooked. And this final screw is basically what you'll tighten to attach it to the output shaft coming out of the robot's 6-axis. And so now we're ready to test. Before we start, make sure to reference my past videos on how to control stepper motors if you are not familiar with them. Otherwise, let's get started. So here I have a super simple Arduino code where I define each of the joints and the pins that they're connected in the Arduino Mega, steps per revolution, speed, acceleration limits, and then basically it'll have some code to enable me to enter the joint I want to move by how many degrees via serial monitor, and we can see that moving in real time. So let's go ahead and try that. So I'm going to do J1, let's try 30 degrees. Later I'll fix the directions. Actually, for me this will be -30. So I'll show what positive 30 actually looks like. I'll change the code later on to have positives in the directions I want them to be. Okay, so let's bring J1 back to 0. Could also do J2. Let's do a 45 degrees. Now I'll do J2, -60 degrees. We can do J3 equals 20 degrees. J3 equals -40 degrees. Let's do J5 equals 90. Let's bring J5 back to 0. Let's do J4 90. Looks like I missed some steps there. Let's do J4 back to 0. Yep. That just means I need to adjust the stepper motor driver VREF calibration. Alright, let's try J6. Let's try 90. So now I'm going to do J20. J30. Now we just tried moving the robot, moving one joint at a time, which is perfectly fine. But what if you want to model the moves before you execute them and see it visually? Well, for that you can use Robot Operating System 2 or ROS2 along with Arvis and MoveIt to model your robot using the already existing 3D models you have. Model the movements along each joint, see it in 3D, and then go ahead and save the motions via waypoints and execute them on your Arduino. So I have the robot on Arvis and MoveIt within ROS2, my computer, and I'm going to go ahead and model a series of movements to use the gripper with the robot to grab a cup that's going to be filled with cotton balls, and then it's going to move it to a position to pour it on another cup. So I'm going to model this, and then we're going to go ahead and save the output and execute it on the robot. Now I have all the commands from this simulation we just ran into a text file. Now the Arduino Mega doesn't have a lot of memory, so I can just store them all at once and go execute them. So I have two options. I could send the commands via serial communication from a computer to the Arduino Mega, or I could save all the commands in an SD card that the Arduino Mega gets to read. Now again, due to low memory, it cannot read them all at once, so it's going to have to read them in batches. Read a set of 30 waypoints, and as it executes, it reads more, and so on. Reading the movements that it's about to execute as it executes them. Just reading a little bit ahead of what it's coming. So that's the option I'm going to go with. Alright, so I have this cup with cloth balls that I want to dump into that red cup, and we're going to use the robot to do that. Here's the Arduino code. I'm going to go ahead and pick 3 for the cup test. Hit Y, enter. We'll get 5 seconds before we start. Alright, let's try that again. And here's a different motion planning being executed with the camera attachment. Now here are the things that I don't really love about this robot. Number one, the Arduino has very limited memory. So I could have used another microcontroller or maybe even a Raspberry Pi with the same controller as the RBX1 that would have costed more. But the Arduino itself created a limitation that requires sending commands via waypoints to the Arduino in batches, which added some complexity and it wasn't necessarily as smooth as if we could load everything all at once and go execute it. The other thing is really that joints 4, 5, and 6 are relatively weak. I could have purchased Planetary Gearbox, some Stepper Line or others to make them stronger, but that would have added significant weight far from the base, which could have impacted joints 2 and 3. Overall, the robot's really good, although it was mainly done for educational purposes, right? It's not a robot that you can put into production and long for an extended period of time, but it's an awesome project that I really enjoyed and I hope you do too. That's it for this video. Thanks for watching, and I'll see you in the next one. Bye.